In this lesson, we'll illustrate how a cantilevered beam can be analyzed using the simulation option of ANSYS Workbench. We'll begin a new Design Modeler database and then select inch as the unit of measurement. Next, we'll start by selecting the XZ plane as the sketching plane and then sketch a rectangle, which will then be dimensioned to be a 1 inch by 1 inch cross-section. Now we'll change the view to an isometric view and then click on the Extrude button. In the Details View window, the direction is now set to Reversed, and then the depth will be changed to 4 inches, followed by clicking on the Generate button. Since this completes our solid model, we will now select the Save option and then save the file using the name Tutorial 6.1. In order to begin our simulation, we'll click on the Project tab, and then, after making sure that Tutorial 6.1 is highlighted, we'll click on New Simulation. We will not use the Map of Analysis Types, so we'll close that window now. Next, we'll change the name of our solid model by first expanding the geometry item in the outline window, and then right-click on Solid and select the option Rename, and then key in the name Beam. We will now double-check that our material type is structural steel. This is done by clicking on Beam in the outline window and observing in the Details View window that the material type is listed as structural steel. The analysis type is next defined by clicking on the drop-down button, New Analysis, and then selecting Static Structural. Note that in the outline window, a new folder has appeared, which is named Static Structural, and it includes a question mark. This is because we have not defined the loads or boundary conditions yet. We'll begin the process of defining the 500-pound load at the end of the beam by first selecting the Static Structural folder in the outline window and then rotating the beam so that the Z-axis is vertical. Next, after making sure that the selection mode is set to Face in the toolbar, we'll select the end of the beam. Now we'll click on Loads and then select Force from the drop-down menu. In the Details View window, we'll now change the way in which forces are defined to be components, and then enter negative 500 pounds for the Z component of the force. Our next step is to define the support or boundary conditions, which will consist of fixing the opposite end of the beam, so we'll rotate the beam so that we are looking at this opposite end. The support is defined by first selecting this end of the beam and then clicking on the Static Structural folder, followed by clicking on Supports in the toolbar, and then selecting Fixed Support. The last parameters that we have to define are the types of results that we wish to calculate. This is done by first clicking on the Solution folder and then selecting Deformation, followed by Directional. In the Details View window, we'll now change the orientation to be Z-axis, since this corresponds to the direction of the load. Since we also wish to calculate stresses, we'll now click on the Stress button, followed by selecting the Normal Stress option, and then in the Details View window, identify the orientation of the stress to be the Y-axis. Since the beam is now completely defined, we'll now click on the Solve button in order to start the analysis process. We'll now save the analysis before we begin investigating the results. As you can see, the normal stress results are currently displayed, along with the stress values displayed in contour bands on the beam, We can also make use of the probe option in the toolbar in order to display results at specific locations on the model where we click. We'll now click on the label icon and then select one of the probe labels, followed by pressing the Delete key in order to remove the label. In the outline window, we'll now click on the Directional Deformation line in order to display the deformation contour bands. We will also illustrate how the undeformed wireframe image of the model can be superimposed on the display, as well as how the multiplier of the deflected shape can be changed.